Yep, thanks Dr. Gebhardt for that introduction. Thanks everybody coming out to Swine Day this year, and thanks for the professors for allowing me to speak on some of the research I've been focusing on during my PhD in the last year and a half. So when we go back to during the COVID time, producers started noticing incidences of lameness in the growing and finishing period. And this lameness can cause removals, mortality. So then producers started working with diagnosticians and really wanted to figure out what was causing this issue. And before they could figure out what was causing this issue is, we really didn't know how to measure for bone mineralization. We can draw blood, look at calcium and phosphorus in the blood. We can attempt to get urine and look at urinary calcium and phosphorus, or collecting those bones and measuring for bone mineralization. So after all the producers and diagnosticians started talking together, the Minnesota Pork Board put out a call, and their call wanted to look at bone mineralization within the nutrition research priority. So myself and the professors put together a grant, and we wanted to establish baseline estimates for several different biological measurements that are used to measure bone mineralization within growing pigs. And to do this, we really broke up the grant into two studies. We did two prospective studies, one in the nursery and one in the finisher, where we wanted to feed different levels of calcium, phosphorus, vitamin D, phytase, and create a broad range of dietary nutrients so we could find differences in bone mineralization, analyze those bones so we could pick up differences. And after we went through collecting all that information, we conducted a diagnostic survey where we went to producers across Iowa and Minnesota, went to their sites, collected samples, brought those in, and analyzed those samples as well. So first we'll go through the nursery perspective study that I conducted. We conducted this study out at our Kansas State nursery facility. We had 350 pigs. They were used in a 28-day study ranging in that kind of phase 3 from 25 to roughly 60 pounds. And we set up 6 dietary treatments for the study. This table outlines the treatments that we use. So starting with the phosphorus deficient diet, we wanted to have a really deficient phosphorus diet so we could find vast differences in the bone mineralization. So we used 57% of the NRC recommendation for this weight range for the phosphorus. We had 1,653 IUs per kilogram of vitamin D in the diet. This is what we would have in our KSU premix. We consider this the industry levels of vitamin D that are fed in diets. And then we had no phytase included in the diet, so we were meeting those phosphorus requirements only using monocal in the diet. And then our next 2 treatments, we fed 100% of the NRC recommendation of phosphorus for those for the weight range. We kept the same industry levels of vitamin D in the diet. And then we had 2 different levels of phytase. So we did not include phytase in the first treatment. So once again, meeting that phosphorus requirement by only using monocal in the diet. And then we included 2,000 FYTs per kilogram of phytase, given a 0.14 standardized total tract digestible phosphorus release. And then the final 3 treatments, we fed at industry levels of phosphorus in the diet. So this would have been approximately 130% of what that NRC requirement is. So increasing that level of phosphorus, hoping to find an increase in bone mineralization. We kept phytase constant in the diets. And then we had 3 different levels of vitamin D in the diet. The first, we included no vitamin D in the premix, and then industry levels of vitamin D, and then industry levels of vitamin D with high D added on top of that. And the high D would have provided the equivalence of 2,000 IUs per kilogram of D3 in the diet. So once we fed the diets for 28 days, 8 pigs per treatment were euthanized for collection of blood, urine, and serum. The bones that we ultimately decided to collect for the next 3 studies that I'll talk through are the metacarpals, and we would have used a 3rd metacarpal for all of the analysis, 2nd rib, 10th rib, and fibula. And what we were able to do was collect both the left and right side of the pig. So when I go into some of the analysis later, we can do different measurements on the exact same bone from both sides and look at the difference in procedure and what those have on bone mineralization. So for the blood, we analyzed serum chemistry, and this would have been a full large animal workup panel that Iowa State does. We mainly focus on calcium and phosphorus, but they have a panel that measures around 20 different things within that serum. And then 25-OHD3 and 125-OHD3. In the urine, we analyze for calcium, phosphorus, and creatinine. And then for each individual bone, we analyze for histopathology of the second ribs, 10th ribs, and fibulas, so extracting those growth plates from those ribs and looking at those under a telescope or microscope to look at the growth plates for lesions and fractures within those growth plates. DEXA scans were used, so taking an x-ray of that bone to measure bone mineral content and bone mineral density. And then I measured bone density another way using the Archimedes principle, so looking at water displacement of that bone. Breaking strength, bone ash, both the non-defatted and defatted method, and then taking that bone ash from the defatted bones and analyzing that ash for the amount of calcium and phosphorus content within that bone. So we'll start to move in some of the results for this nursery study. Along the x-axis, we have the treatment layout of what the 6 individual treatments were. Here we're looking at serum calcium and phosphorus. On day 0 of the study, we were able to bleed 8 pigs so we could get baseline levels of what the serum calcium and phosphorus were in those pigs. Those pigs would have been fed regular phase 1 and 2 diets, so adequate in all nutrients. So if we look at the dark shaded bars, that would be the serum calcium in the blood. We observed no differences across treatments, which is what we expected. We were not trying to make these pigs deficient in calcium. And then when we look at the light bars, we see that pigs fed the deficient diets had reduced serum phosphorus compared to the pigs fed NRC or industry levels of phosphorus, but we did not increase the serum phosphorus when we go from NRC levels of phosphorus up to the industry levels of phosphorus. Now looking at 25-hydroxyvitamin D3, so this would be the inactive form of vitamin D in the serum. As expected, those pigs that were fed no vitamin D in the premix or in the diet had the lowest levels of this inactive form of vitamin D, and then pigs fed the industry levels with high D added on top had excess levels of vitamin D in the serum compared to the other treatments, with the pigs fed industry levels all being intermediate. And then looking at the active form, or 125-dihydroxyvitamin D3, as expected, when we fed a phosphorus deficient diet, those pigs had excess levels of the active form of vitamin D, so they're making up for that deficiency that they had in phosphorus by having higher levels of vitamin D in the serum, the active form. And then, as expected, the pigs that had no vitamin D in the diet, they had the lowest levels of active vitamin D in the serum, with the other treatments being intermediate. So now we'll move into some of the bone analysis that I worked on for this study. Here looking at both the non-defatted and defatted method across the treatments. So as we increase phosphorus in the diet, we start to increase the amount of bone mineralization in those bones by increasing bone ash. But it's more important to look at the 2 different procedures that were used. In the light bar, we see these were bones that were used with the defatted method. So when you defat a bone, you will stick it in ether for 7 days, and that pulls all the fat and water out of those bones, and it more standardizes the bones rather than non-defat, where you just dry those bones, put it in a muffle furnace, and then you have the ash. So when we look at the difference between regardless of treatment and regardless of what bone you're using, you see anywhere of a 10 to 12% increase in bone ash percent when the defatted method was used compared to the non-defatted method. So we didn't pick up a huge difference in treatments, but the difference in procedures is almost 4x the difference that we saw when we across the 6 treatments. So then when we take the defatted bone ash, we digest it down, and we analyze that for calcium and phosphorus. So here, as we increase from deficient levels of phosphorus up to industry levels of phosphorus, we increase the amount of grams of calcium and phosphorus that are within that bone ash. But when we look at it on a percent basis, so the percent of grams or percent phosphorus as a ratio back to the ash weight, so how much that ash weight weighed, we see no differences across treatments. And this is because as we increase bone mineralization, we increase the amount of calcium and phosphorus within that bone, but we're also increasing the size of that bone. So we would expect to see no difference in looking at percent of calcium and phosphorus compared to when we look at the actual amount of grams of calcium and phosphorus within that bone. And finally, for histopathology, we would have taken these bones up to Iowa State and they would have cut off the growth plates and put them on slides and analyzed each individual growth plate from the bones. And they used a scale of 0 to 3, 0 being a normal bone, and then 3 being a severe or extension of this cartilage tongue extending into the metaphysis. So we see this cartilage is not getting turned over into bone as it moves down into the rib. And this is what we would typically see with incidences of bone metabolic disease. And another interesting thing to point out with this histopathology is typically when we send a pig into the diagnostic lab, it's going to be a sick pig that was either euthanized or died. So they typically see these types of scans when they're measuring histopathology. They typically don't see a normal scan when they're going in with cases of bone metabolic disease. And then also for histopathology, as we would have expected, the pigs fed the phosphorus deficient diet had an increase in the accumulative physial grade, so they had more incidences of these severe extension of that cartilage down through the bone. So that was the nursery study. We conducted a similar study in the finisher where we had 880 pigs, and we would have fed these diets for 112 days from approximately 80 pounds up to market weight, so 295 pounds. And we had 5 treatments for this study. Similar to the nursery study, on the last day of the study, we collected 9 pigs per treatment and collected all the same samples and analyzed those samples the exact same as we did for the nursery study. One thing to point out for the finisher study is when we went in to collect these healthy pigs for the study, there was also sick pigs that were not going to be able to go to market. So we collected those sick pigs and collected all the same samples and analyzed those samples the exact same way as we did for the healthy pigs. So this is the dietary treatments that we used for this study. Very similar setup to the nursery study that we did where we fed a phosphorus deficient diet with no phytase included. NRC levels of phosphorus, one without phytase, the other with phytase. And then industry levels of phosphorus with phytase in the diet, industry levels of vitamin D, and then increasing with high D in the diet. And for this would have been the first phase of the study, so from approximately 80 to 120 pounds. And then we stair-stepped the amount of vitamin premix in the diet, so we would have reduced the amount of vitamin D in the diet towards the end of the finishing stage. So moving to some of the growth performance for this study, similar to the nursery study, when we have high D included in the diet, we increase the amount of the inactive form of vitamin D in the serum, and then feeding industry levels of vitamin D, we saw no difference between those treatments. It was important to point out that once again, we were able to collect baseline levels on day 0, and we were able to reduce the amount of vitamin D in the serum due to stepping down the amount of vitamin D in the premix. Looking at bone ash percent, again, the non-DFAT and DFAT method. In the light color bars, again, we have the defatted bone ash method, and in the dark bars, we have the non-defatted bone ash. Here we saw no differences across the treatments, but we do still see that procedures difference with when bones were used for the DFAT method, they were anywhere from 13 to 14% higher in bone ash for the same bone when used for defatted compared to non-defatted bone ash. And since we were able to collect those sick pigs that were not going to make it to market, we were able to analyze those samples and compare the healthy pigs versus the sick pigs. So looking at some of the bone ash data, on the left here we have non-DFAT bone ash. In the dark purple we have bone ash averages from the healthy pigs. And then here in the purple we have the sick pigs. So for non-DFAT bone ash, we saw no difference between a healthy pig and a sick pig. But when we analyzed those same samples using the DFAT method, we were able to pick up a statistical difference with the healthy pig having statistically higher bone ash compared to the sick pig. And the reason for this is we see approximately the same amount of magnitude and change of 1.5 to 1.8% increase in bone ash, but the important thing to point out is the SEM, or standard error of mean, is higher for the non-DFAT bone ash compared to the defatted bone ash. So when we use the defatted method, we're making and standardizing and reducing the amount of variation between those bones so we can pick up these statistical differences with smaller magnitudes of change between them. And then looking at 25 hydroxy vitamin D3 in a healthy pig, it was statistically higher with almost double the amount of vitamin D in the serum. So in summary, from these two prospective studies that we did in the Nursery and Finisher, for bone ash, like I have pointed out multiple times, it's important to know if that method is being done as a non-DFAT or a DFAT method. When you send it to a bone to a diagnostic lab and look at bone ash, if you get that percent back and you don't know which procedures are doing, you're not quite sure if it's deficient or non-deficient just based on the method that you're using. And those differences between treatment were much smaller than the differences are between the two different procedures. Although I did not show bone density data today, it's a much simpler procedure to do than bone ash. When you do bone ash, you have to clean the bones completely, dry them, or put them in the Soxhlet machine, and it can take anywhere from 7 to 14 days just to get that bone ash response back, or the bone ash percent. For bone density, all you do is clean the bones and weigh it, take all the water out by putting it in a vacuum for 4 hours, weigh it again, and you get your bone density result. So you can get a result at much faster rates. And it was easier to detect phosphorus differences within bone ash, specifically in the second ribs and fibulas for the Nursery and Finisher study. And then looking at the amount of bone calcium and phosphorus, for grams of calcium and phosphorus, we observed a difference between the phosphorus-deficient treatments and the non-deficient treatments, but when we look at that on a percent calcium and phosphorus basis, we see no differences across the treatments. And then for histopathology, the 10th rib was the most sensitive, was more sensitive than the second rib for looking for lesions within those bones. So after we wrapped up with the Nursery and Finisher study, specifically the Finisher study where we were able to pick up differences between a healthy and sick pig, we were excited to start the diagnostic survey. So for this survey, we had 194 pigs across 64 commercial sites within 14 different production systems. And at each individual site, we collected a clinically normal or healthy pig, a pig with evidence of clinical lameness, and then a pig with history of recent low feed intake within a hospital pen, which would have been our sick pig used in the study. And for all of these pigs and bones and blood and urine, they would have been analyzed the exact same as we did for both the Nursery and Finisher study. So going into some of the results for this study, I'll use box plots for a lot of the data information just so we can see that spread in data throughout the different results, and kind of as a refresher to understanding how to interpret these box plots. So the line would be the median within the box is either 75 or 25 percentile within that range. The whiskers go down 1.5 times that interquartile range. And like this diagram here, if there's a point that exceeds that whisker, it would exceed 1.5 times that interquartile range. So looking at some of the information that was collected across the 14 different production systems, here being serum 25-OHD3 or serum vitamin D. Across the x-axis, we have the 14 systems that participated in the diagnostic survey or sent samples in for us to analyze. And based on the data, we see quite a distribution of the serum vitamin D within the different 14 systems, with some values reaching all the way up to almost 75 nanograms per milliliter, and some values all the way down almost at 0. And for reference, diagnostic labs, anything from wean all the way up to market. The reference value used for vitamin D would be about 18 to 30 nanograms per milliliter. So if we look from approximately 18 to 30 here, there was a lot of pigs that were below that reference value and a few pigs that were above. And one thing to point out for these box plots, within each individual system, this would be the average of the sick, healthy, and lame pigs all together across different stages of production. So looking at taking that data from the systems and breaking it out into the three individual pig types, we have the healthy on the left, lame pig in the middle, and then sick pig on the right. And we see that the healthy pigs had statistically higher serum vitamin D compared to the sick pigs being the lowest and the lame pigs being intermediate. Now looking at serum phosphorus, again, not as much of a distribution as we saw within the vitamin D, but there are some values that are well below 5, and then some values that reach up to 12.5 or 13. So these values that are low are very, they do not have much circulating phosphorus within that serum. And then looking at the three different pig types for serum phosphorus, we see that healthy pigs were statistically higher than both the lame and sick pigs, with no difference between the lame and sick pig when looking at serum phosphorus. And then finally looking at serum calcium, calcium within the pigs is very tightly regulated. So when we see these very low levels of calcium, we know something is wrong with these pigs. So more than likely they've been off feed or they're sick, not consuming much feed, to cause these calcium levels to be very low across the different systems. And then looking at the pig types, once again, healthy pigs had the highest levels of serum calcium, with the sick pigs being the lowest, and then lame pigs being intermediate. And then now moving into some of the urinary data, I'll show the urinary phosphorus and urinary creatinine data. So here we have urinary phosphorus, so how much phosphorus is being secreted within that urine when collecting the sample. We see that the healthy pigs had the lowest amount of urinary phosphorus being secreted, the sick pigs being the highest, and the lame pigs being intermediate. So when we started to look through this data, we were trying to put our fingers on like why were the sick pigs secreting so much more urine than the healthy pigs. And it really correlates well to the amount of creatinine that's also being excreted from that pig. Again, we see the same trend with the sick pigs having the highest level of creatinine being secreted, healthy pigs being the lowest, and the lame being intermediate. Creatinine is used within muscle tissue growth, and when we start to, the sick pigs that are not eating, they're starting to go through catabolism, so breaking down that muscle tissue to use it as an energy reserve. So then the excess creatinine that they have and the excess phosphorus is all being excreted out in the urine. And then looking at some of the bone ash differences, here looking at defatted bone ash for the different pig types. We do not have any statistics ran on this slide, but we see that the healthy and lame pigs had slightly higher defatted bone ash compared to the sick pigs, with relatively low standard deviation or distribution within those three different pig types, showing again that when we defat the bones, we reduce the amount of variation within those bones, unlike the non-defat, which would have higher standard deviation within the three different pig types. So this diagram shows the difference in the two bone ash procedures across the three different pig types. So on the left here, we have the healthy pig with the defatted bone ash, non-defatted bone ash, the lame defat, lame non-defat, and then sick defat and sick non-defat. And again here, it's important to point out the magnitude of change between the three pig types is not that large, but the big difference is between the two different procedures used, with the defatted having anywhere from 10 to 11% higher bone ash compared to the non-defatted bone ash. So some of the take-home messages so far from the data that I've shown today of this diagnostic survey is the bone ash differences between the methods are larger than the differences between the three different pig types. We observed clear differences in serum vitamin D, serum calcium, and serum phosphorus between the three pig types, with the healthy having the highest values and the sick pigs having the lowest values of those different serum analysis that we measured. And finally, when looking at that urinary phosphorus, the sick pigs are excreting a lot more phosphorus and creatinine than their urine, and this is a result as a decrease in the phosphorus being used for lean tissue deposition. So now moving into one last study that I conducted this year, based on some of the results that we had from the survey, looking at different phosphorus and calcium levels and bone mineralization. I collaborated with PIC on a study where we looked at using recommended levels of their phosphorus requirement, or 75% of their recommendation, and then different levels of calcium and phosphorus, so 0.9 to 1, 1.3 to 1, and 1.75 to 1. And one thing to point out is the 75% of recommendation is pretty close to the NRC recommendation for phosphorus. This recommended phosphorus levels would be for maximum lean tissue growth. So looking at some of the data for final body weight for this wean to finish study, we observed a calcium by phosphorus interaction. So pigs fed 75% of that recommendation of phosphorus. As we widen that calcium to phosphorus ratio, we reduced the final body weight from about 10 pounds from the 0.91 to 1.75 to 1. But when we feed the recommended levels of phosphorus, as we increase that calcium phosphorus ratio, we start to linearly increase final body weight. And we see the same result when we look at bone mineral density. So for these pigs, we would have sampled metacarpals at the packing plant and analyzed them for bone mineral content. So again, using that DEXA scan, taking x-rays of each individual bone to measure bone mineral content. And again, we see that same interaction where within 75% of the recommendation, widening that calcium to phosphorus ratio, we reduce the amount of bone mineral content or reduce bone mineralization, while when using recommended levels of phosphorus, as we increase or widen that calcium phosphorus ratio, we increase the bone mineral content. So with that, I would like to thank a lot of sponsors that were able to make this study get done. First, the Iowa Pork Producers Association and the Minnesota Pork Board. They were the one that funded the grant. The Minnesota Pork Board funded the Nursery and Finisher study. The Iowa Pork Producers Association funded the diagnostic survey, as well as DSM for providing insight and helping get this study conducted, helping analyze a lot of the vitamin D analysis that we did. And then collaboration with both Iowa State and Kansas State Vet School. They have been great to work with and providing insight on everything that we've analyzed throughout this study. And then the 14 different production systems that were used and helped for the diagnostic survey. I don't think I would have been able to go around and sample all the pigs that were used in the study. So a lot of the veterinarians and nutritionists went out and collected all the samples and shipped them down to K-State to analyze. So with that, I will hand it off to Jordan.